Another draft physics presentation. Draft science, whatever. Draft physics, the video, .com, so the website. DraftScience, the YouTube channel. Anyway, just, it's the way it worked out. Yeah, if you get one, you can't get the other, kind of thing. But anyway, so sorry, I have a back misery. Anyway, so I've been watching a bunch of these old videos, from the 50s and 60s, instructional videos, some made by companies like General Telephone and stuff, kind of funny. So very self-promoting and lots of other crap, but little bits of useful information. And then some of the MIT style videos. This one sort of looks like an MIT video, but I'm not sure that it is. And they have exactly the same experiments, like they're doing now in lectures in colleges. And it's just kind of funny that they haven't advanced it much. I mean, obviously they're using integrated circuits and stuff like that to create the audio signals or something, but I mean the basic experiment is done exactly the same way, and without any changes or modifications, or showing what if we do this and what if we do that. And it really is part of the problem with this physics science is they find an experiment that verifies a theory, and they really don't want to unverify it by confusing it with any kind of, well, what if we do this and it does something, and they really just don't want to know that it does something that just doesn't fit with the story they want to tell. That's my interpretation of it. It just seems kind of obvious that over a period of 60 years, when you have this equipment sitting in front of you, that you would play with it and see different results messing with it in different ways. And it seems like they just don't nobody finds that at all interesting, which is very suspicious. Just as a obviously nobody's encouraged to find a flaw in the underlying assumptions. Apparently there's no reward for that. I can imagine that some student might have done something and said, look what happens, it's completely different if I do this and this. And I could just imagine a professor saying, yes, well, that just doesn't have any instructional value. Something like that. Not rewarding it. Anyway, that's not exactly the premise. I mean, the thought schema I wanted to go into this video with. It's very interesting, and it just gives me an opportunity to highlight some simple concepts. Again, this is how old they are, and they just haven't advanced the subject at all in 60 years. Just nothing, no improvement at all. So this might take a while. It might take 2 parts. I have sped the video up, and lots of it is boring, and I'll probably talk too much and blah blah blah. But anyway, yeah, this is definitely an MIT video. Just remember, in the end of the video, it would have to, Massachusetts Institute of Technology, MIT. Probably don't need this part. But there's an antenna, it's sort of a part of the story here. How do I get 2 standard?
You're on portion on the glide path of 090 ahead.
This is really funny just because I grew up, when this is how the world looked. It really did look black and white, actually. It really did.
On portion on the glide path 090 heading, final cockpit check compass. You now over shake us down on portion on the glide path, take over, complete your full stop landing.
My mother actually worked for American Airlines, but she was too tall to be a stewardess. So,
you have seen several examples of an electromagnetic disturbance traveling through space, from a source to a receiver. In this film, we propose to show you that all these disturbances are electromagnetic waves.
This is like Jack Webb's little brother. I mean, this guy has got to be the most... I mean, he's very nice. It's just fine, but I mean, it's just, it's just so stiff, so stiff.
We frequently indicate these waves pictorially. Notice the range of wavelengths. Radio waves, about a meter. Microwaves, 1/100th of a meter.
So 1/100th of a meter. So radio waves a meter, microwaves 1/100th of a meter. This is so this is the real part that's kind of interesting, is that most charts don't show you the distance of the wavelength in the chart, in any kind of way to make it really grokkable. But you're talking about going from these FM radio waves in this range, TV, and then microwaves, just a few centimeters, and then when light is just impossibly small by comparison. So it's a huge change in the mechanics of this thing, this mechanism.
Infrared, about 10 to the minus 5 meters. Visible light, 5 times 10 to the minus 7 meters. Ultraviolet, about 5 times 10 to the minus 8 meters. X-rays, 10 to the minus 10 meters.
So it's a million times smaller, well, 1,000 times smaller, I guess, per zero. What?
You have just seen the enormous range in frequency or wavelength over what we call the electromagnetic spectrum. You might think that because of this wide variation, that these are different effects. Nevertheless, we believe that they are all basically the same.
Right, and it's kind of true, but the real catch is there's not the same mechanism for producing them. So when radio waves are being produced by an electric signal that you're creating the wavelength with an electric signal. So an electric signal is doing the on-off. So it's just blinking, on-off, on-off, on-off. Switch flipping, on-off, on-off, on-off. And that is creating the radio waves that emanate from the material. And those radio waves, are actually made out of what are called photons. So somehow we're creating the pieces of the photon. So this is how I would illustrate the reality. So I'll just switch to this drawing thingy. So yeah, I wanted to pre-draw these, but I just couldn't think of exactly how to do it, so I said, oh, fuck it. But by what I'm arguing, a photon is its wavelength. That is, it's the thing we mechanically. There's a lot of papers in kind of the wrong position. Anyway, that this defines a photon is a frequency between what would be called the particle. The particle itself doesn't have a wavelength. It's the distance between the particles that defines the wavelength. And so even if you don't believe that, whatever you believe of an emanation is, the point is when it's radio, we're creating it by stimulating the electrons with electricity at an interval. So we put in a frequency, and geez, I'm gonna move that, Gary. Yeah, okay. Yeah, I'm sorry. I sometimes I'm off of my drawing table. I have to find some standard way to do this. So anyway, we put in a frequency, and the frequency we put in causes it's converted into the release of these force bits. And I would argue these force bits are the same force bits that make up magnetism and make up gravity. So, and when they're at a frequency, though, we call them electromagnetic waves, but they're really just the same particles, just in a form that's wave-like. So radio, we're creating completely in phase what could be called waves, because we're taking a bunch of these things all at once, and then a bunch all at once, and a bunch all at once, and a bunch all at once. So there's no phase issues at all, because everything is created by the same input signal, and it all is stimulated at exactly the same moment, so it just becomes a wave. So it's very sensible to call it a wave, because each little soldier is exactly lined up, and these are just like waves of bullets or any other physical thing you sort of describe as waves, even the ocean waves. it's very much like waves, because all the particles are forced to do exactly the same thing, to line up exactly the same way. But in things like, so once we get to, the high gigahertz kind of frequency, so really small wavelengths, below, less than a centimeter or less than a millimeter, of distance between the force bits. Once that distance gets small enough, we have no mechanism for creating that. We can't vibrate something without breaking it, without vibrating it into little pieces. If we try to stimulate anything with a frequency that high, the frequency itself will just destroy the material, so it can't produce this kind of effect. So all we can do is create a system where we create some kind of matter that's in a special condition, so that when we stimulate it with any kind of frequency, any kind of vibration, it will release photons at a consistent frequency. But the catch is it not necessarily releases them at all the same moment. It'll release them at different moments in time, so they will not be in phase. They won't be like this. They won't be in nice straight bars. They'll be in they won't have the same coherency. They'll be somewhat coherent, maybe at best. In a laser beam you get some coherency, but it's still far from perfect in phase soldiers like this. But it's an important distinction to recognize that we can't create photons the way we can create radio waves. We can't define their frequency. We have to let atoms release them through a process where we stimulate the atoms to do so, and we have no way of stimulating individual atoms from the same location. So that's the other catch to it. So you have to sort of understand, like, say if there was atoms inside a material, they could be in different positions, and so when they release their little bits, they release them from different positions. So quite obviously the ability to be in phase would be disrupted by the fact that obviously I should have put this bit maybe here, that their starting point would be different, so each wave would be out of phase in the sense that each bit would have a different starting point. So none of them could be in phase because they start from a different location in real space, which is also a problem. Where the radio waves are essentially being thrown off the surface, so they're all from the same location fundamentally. They'll all have the same starting position, and with radio waves it doesn't really matter whether frankly, even if the photon, the little force bit, is coming from the middle of the antenna is a tiny percentage of the meter thick wavelength. So obviously a few inches isn't going to make much difference in a meter long wave, where in the case of the photons at nanometer distances, tiny differences in the surface would be complete wavelength changes. So it's, to think of it all as the same thing, it's right in the same, it's made out of the same stuff, but these different manifestations of the spectrum are created by very different mechanisms, and they just don't emphasize that enough. In comparing one to the other and saying, here's the same phenomenon, look, we're looking at the same phenomenon. It's really not at all the same, and it has very different causes for the effect. So just want to emphasize that. They should know that it could have, let's just say, right? Because I have to just pretend that this doesn't fit perfectly. So of course, to keep pretending you don't understand, at least you don't, and it's depressing. Anyway, back to the fun.
What do we mean by this? Simply this. If we take any frequency from the spectrum, we will find the same physical properties demonstrated there as we would at any other part of the spectrum.
say same physical properties, and they're really the what the little bits are is going to be the same. They're just going to be at a different frequency. But again, creating them, they're going to be created by very different mechanisms with very different tolerances.
We're going to investigate the electromagnetic spectrum by doing some experiments showing these common properties. Now, what are these properties? First, the transmission from sender to receiver goes as a wave.
Yeah, it's great handwriting.
This means we expect to find familiar wave properties. Secondly, the waves...
Right, so again, it's just an obsession with waves. I mean, they have a frequency between them, and there's another word for that, a period, and wavelength. You can use these three words, frequency, period, wavelength, all to describe one thing, which is really how often the brain of the thing, the significant bit, passes as time passes. So you could just say, let's just give it an arbitrary significant bit, and you're just counting how often the significant bit goes by, however you define the significant bit. I'm just saying the model I've given you of the significant bit being a described in a particle form fits without any problems, without any mechanical problems. And again, you wouldn't say bullets wave. It would just be kind of a silly thing to say.
We arise from accelerated charges.
Alright, now accelerated charges is another trick word in the sense that, yes, it's always associated with the movement of charges. Now when they say accelerated charges, all they're really saying is electrons, and protons. But we don't have any evidence that protons are really in this electromagnetic spectrum thing. This is an electron phenomenon primarily. I mean, everything indicates it's an electron phenomenon, one that electrons are sensitive to and the creator of. And so it's to call it electron acceleration when the electron can just be doing this. Accelerates this way, then accelerates that way, and accelerates this way, accelerates that way. It's just moving. So it's a moving electron. It's changing its position. So again, this is a kind of important semantics. So again, they've glued this word wave to it, which doesn't necessarily apply. Now they're saying acceleration is the key concept, as if it has to be moving to a new location in some sort of real directionality, when no, the movement just requires that it's changing its position relative to the proton it's bound to. And that's all. It just has to change position relative to the proton, relative to the other electrons it's bound to. So semantics, but really important semantics, I would argue.
Third, these waves always travel in free space with the same velocity, the speed of light.
Right. Now, again, physics had this choice. Maxwell kind of decided for everybody that this is what we're going to call things. But again, there was this choice. There was this observation that these other forces move at the same speed as light. Light was the thing they decided went a speed first. They understood it to move at a speed, and then it took a while to get gravity and magnetism to figure out that they were doing the same thing. And so instead of just saying generally speaking, it's the speed of force. I'm just saying these are, again, it's semantics, but it's really important semantics, because it needs to be understood that light is a force. It's just like the other forces, and just happens to be one that we can personally interact with just one little piece of, with our eyeball. I mean, you could argue that, we could sense some force effects that, like our hair somehow isn't absorbing as much gravity as, the gooey parts of ourselves. We can sort of get some idea of how volume, affects how much force you can detect. You can't detect as much gravity with hair as you can detect with, say, the rest of your body. Something like that. You can't absorb as much. I mean, detecting, again, is a tricky word. I mean, maybe you can detect more with your hair in a non-atmosphere, but whatever. I'm not I'm just arguing that this semantics is really important to doing a really explicit physical science. So I'd say that we have 3 axioms there, and they're all, dangerously flawed if they were taken too literally. Wave, it's not a wave. It doesn't have to be. It's a frequency. The force comes at a period. Acceleration of charges, acceleration of electrons. So again, charge is electron. So we're just talking about the movement of an electron. And then speed of light, no, it's speed of all the forces. It's going the same speed as the other bit forces that exist. So again, these are just, and this 70-year-old mistakes, and they just keep making them.
4. The waves are transverse. By this I mean that the electric vibration is at right angles to the direction in which the wave travels.
So this is just a way of saying it's polarized. So again, the electric vibration is just an assumption that there's some sort of field that it's vibrating. It has no detail at all. So here it is, it's kind of a premise established based on another ambiguous premise. The premise of the existence of some electrical field or magnetic field that somehow this photon is oriented to. When all you really need to say, technically, is that the force has a shape, has a polarization, and that it's polarized no matter what it comes from, it's polarized. And the argument I would make in defining what polarization is recognizing that once you understand this thing is defined by I have to remember to switch to the drawing, Gary. Okay, still haven't found a simple way to do that. So the only the way to understand this is that, okay, so if I were to write premises, what the premises are is that every manifestation of the electromagnetic spectrum requires there to be 2 of these things. That's as a minimum. 3 or 4 can also be coming on the same path, but they're required to be at least 2 of them for you to recognize it, because you have to recognize it by recognizing the distance between the significant bit. And the argument I would make is what polarization is a reflection that these 2 aren't necessarily on a perfect line, that they're actually, when they're admitted inside the material, very small materials sometimes, big materials other times, that they're staggered in their position a little bit. They're not all in perfect straight. They're not in the same plane in one dimension. So you could just understand that as they can be on different points on the plane. They can come at different positions, but it has to be on the same plane, I guess I would argue. Is the same, they'll be in different locations on one plane of one dimension. Don't know quite how to see it. Again, it's very difficult to draw that perfectly, but the idea, when it's coming at you, say if this was the ton and the other ton's coming here, or the other ton is coming here, they're on some line that you could draw that they're coming at you from. So it's never so it's just polarization. So that's, I just want to make that distinction, that all he's really saying here is that they're polarized, in the sense that they're not necessarily on a straight line. So I just did the straight line thing. They can be, and I think that's what they call circularly polarized, is that they're lined up perfectly. But usually they'll be polarized in the sense there'll be some unevenness in exactly how lined up they are in the plane that they're flying in. Okay. Yeah, I think that's good enough. Why don't you let him write it first, Garrett? Well, yeah, I didn't even let him write it.
And finally, that these waves can be polarized.
See, same thing. So the transverse part is basically saying the same thing as the polarized part. Now you could argue he put number 4 there, the transverse part. He put that in there because of Maxwell's laws and because of what we observe, is that when the charge moves, it radiates a force, the electron, this is the electron moving, it radiates the photon, the energy, perpendicular to its movement. So whether you're making a radio wave or you're making light, the electrons are moving this way if the light's coming out this way, or they're moving this way if the light's coming out this way. But it's perpendicular. The movement has to be in this dimension for the photon to be emitted in this direction. And the electron goes this way, then the photon is going this way, or this way, or this way. It's always tangential, perpendicular to the acceleration. So that might be the tricky part. Is, number 2 is the accelerating part. Number 4 is the transverse part, where he's just saying he says this electric field thing, but what he should have said is that the energy will be released perpendicular to the movement direction, the acceleration of the charge. And again, the charge doesn't have to move anywhere. It just has to, move anywhere far. It just has to move, and then can move right back again. So we're just talking about electrons moving out of position and then moving right back into position again. This creates photons. This creates electromagnetic radiation. Just having an electron move like that. So this really doesn't have to do with something you think of as acceleration. I mean, clearly that's an acceleration, but it's one that's going to be eaten up by the tension that's going to move it right back again. It's inelastic or elastic. I hate that word.
And this property is related to the fact that they are transverse.
So he tied the two together, but the real fact that that's related to is the acceleration fact. I don't think so. Maybe later.
We mean when we say they can be polarized, that we can select any plane containing the direction in which the waves travel, and can force the electric vibration to lie in that chosen plane.
Now, he means by force, usually means forcing them to go through a filter that will alter the polarization. So that's the polarization filters are actually changing the polarization of the light in the light. So I would again use my jail bars analogy, which I think is perfectly analogous, and you can understand that frisbees that you can make a special set of jail bars where if I'm throwing frisbees on edge, trying to get them through the jail bars, that some of them can be a little bit crooked and they'll hit the edge of the bar and bend straight. And that's basically what a polarizing filter is doing, is allowing some that are off to still get through because the bars are far enough apart, but something this way won't get through. And incidentally, of interest, some that are perfect in alignment still won't get through because they'll hit the actual bars. Another fact that these people don't pay much attention to.
Now, some of these properties can be determined fairly directly. For example, we can easily measure the speed with which the waves travel. We've done this for you already with visible light. Other properties, such as the wave nature, the fact that these waves arise from accelerated charges, and that they are transverse and can be polarized, must be inferred a little more indirectly by doing it.
Right. So again, he's conceding they've inferred, from indirect evidence. But I would argue that they didn't do the inferring thing. They did the aggressive jump to the conclusion thing. It wasn't like it was an open question and they were looking for the right answer. They were looking for a specific answer and aggressively clung to anything that rewarded that. So it's like somebody going, you hide something, and then somebody goes out and looks for it, and everybody yells, you're getting warmer, you're getting warmer. They were guided by a notion of what warm was, and warm was anything that confirmed wave theory, and cold was anything that confirmed particle theory. They ran from it aggressively.
Experiments whose results depend upon these properties. We're going to investigate the wave nature by doing some similar interference experiments in the radio wave region, the microwave region, with visible light, and in the X-ray region of the electromagnetic spectrum. We've chosen an interference experiment because you are already familiar with this as a wave phenomenon. Along the way, We'll show
Yes. So again, so this was one of the things where again it's just this premise that this simplest pattern in the world, on off on off on off, means interference, and therefore we know this is interference, and there's nothing else that could possibly create this pattern, and blah 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 blah, and a completely, that's really bad assuming.
The waves are transverse, that they can be polarized, and that they arise from accelerated charges. We'll start first with visible light. You're already familiar with this as a wave phenomenon. But before I do the interference experiment, let me show you that visible light arises from accelerated charges. This room houses the MIT synchrotron. Usually, when we observe visible light, we do not see the details of how light is produced. This is because the light is ordinarily emitted by charges whose motions are on an atomic scale and too small to see. However, there is one example.
This part isn't terribly helpful, but I'm not going to jump ahead. I mean, this doesn't exactly show how moving charges create light, but whatever, I think they just wanted to show off their cyclotron.
Which visible light is emitted by charges moving on a large scale, where we do understand the detailed motion of the charges. This occurs in the high-energy electron accelerators used in nuclear physics. Behind all this hardware is a large, circular, highly evacuated tube, which looks like a donut, and in which electrons travel in circular orbits with very high speeds. Large magnets are used to deflect the electron paths into circular orbits within the donut. If you could look inside the synchrotron.
And what they're really doing is pushing them in, like gravity would push something, like gravity would push the Earth in or something. So they keep pushing them to a tighter radius, and that creates the higher energy.
The donut would look something like this. You recall from work on circular motion that a change in the direction of motion implies a radial acceleration, a centrifugal acceleration. Now, if accelerated charges radiate electromagnetic waves, we expect that the centrifugal acceleration of electrons in the synchrotron will result in the emission of electromagnetic radiation, in this case, light. There is a porthole in the donut which allows us to look.
So it's not a great illustration, but he's pointing out that we're in the cyclotron, what they're really doing is pushing the electrons, they're accelerating them in towards the center of the donut. And so that's where the energy is going in. So that's where the movement of the electron is down towards the center. So the emission of the photon would be perpendicular to that downward motion, so it would be shot out in some vector going out of the donut.
The radiated light. You are now looking through the actual porthole at the radiated light. The light flickers because the electrons are injected into the machine in short bursts. The important point, however, is that the light arises from the electrons undergoing a high acceleration as they move in their large-scale orbits.
Right, which don't last too long because the flicker is basically pointing out the electrons are shot in there and blah blah blah. They don't, they don't survive their experience for very long. Cyclotroning, but whatever.
Accelerated charges are emitting electromagnetic waves. Here's the apparatus we'll use for the visible light.
Photons. See, so again, electromagnetic waves. There's no evidence that photons are at all electrical or magnetic, just none. Electrons are electrical and magnetic. Photons are not. There's no evidence they are, and yet they're called a wave in that some kind of medium, and it's not a. I don't think it's even a coherent model. I mean, he couldn't illustrate. They can't draw the pictures I've drawn because they don't have a picture of this photon that is at all coherent to any kind of thing we see in the universe of stuff interacting with stuff. It doesn't have any kind of stuff property.
Interference experiment. This is a carbon arc source of visible light. The light travels through these condensing lenses and onto a slit here. This slit.
So this is before I guess they had any good lasers. They had a cyclotron, but they didn't have a laser. So anyway, two lenses, and then it goes through a single slit, and then it goes to the double slit. So just think about how messy this is in a sense. So first you're taking regular light and you're trying to create a good focus, and then you're putting it through this, which is a pretty monstrous single slit, by the way. But yes, let's go ahead.
Becomes a single source of electromagnetic waves, which travel.
So a single source, but yes, a source that's diverging, okay? And yes, the center piece of that light will be not diverged as much. So he's basically using the slit just to create a small point source of light, which would be the light that goes straight through the slit. So the central maxima is what he's sending. So he's sending the central maxima because the rest spreads out. So he's just sending the central maxima to the double slit.
Cross here to a double slit, reaching each of the slits in the same time.
Now, the catch to this part is that the single impediment in between these double slit is a wire. So this is really the single wire experiment, and it's not really a double slit. And so I might as well draw first. Might as well do it before we get too deep into this stuff, because it's sort of important how it is understood. We'll flip this over, save some paper. Alright, so alright, so understand, first it went through the single slit. Let's see, I'll draw it going down, let's say. And so the light diverged from that single slit, but there was the center maxima is the strongest light, and that goes to the double slit. And so the double slit he's created is basically just a wire. So the space is much bigger than the this space is much wider than the central impediment, and so these surfaces are almost superfluous in the experiment. They really don't have any meaning. So what he's really doing is just doing a wire experiment, and that will create a pattern of bars, but it won't be the full double slit experiment, because the bars will not have the traditionally what they're supposed to do is get stronger and stronger, and then strongest, and then strong, and then weaker. They're supposed to do this kind of thing, and that's a true double slit experiment, in where the surfaces are imposing the shell and the wire is creating the bars. Essentially, I would argue, fundamentally, that's how it works. So what I want to argue here, in the video, what he's going to do is he's going to attempt to block one of the slits, which is totally impractical because this is a wire, so I don't think there's any hope he had to do that. But anyway, let's say he did it, and there was just light, a little bulge of light on the other side. Well, it's just a bulge of light because this slit is huge in terms of its width, so you wouldn't get any pattern. Even as a single slit, it wouldn't produce any pattern at all. It's so wide, and the only thing, like I said, that's relevant to creating the pattern was the wire. So he was really just doing a single wire experiment and then pretending to block a slit that wasn't even relevant to the experiment. So it was it's quite deceptive, or whatever you want to call it. I mean, it's just not a very accurate description of the phenomenon taking place. So you can almost see in that image, there's a little tiny wire in the middle. So it looks like a single slit probably to you, because you're not even seeing it as well as I am. But there's just a wire in there, a little tiny wire.
Each of these slits now becomes a new source of electromagnetic waves, with crests leaving the slits simultaneously. These waves radiate out into space in a roughly spherical manner and eventually begin to overlap.
Right, so this is what he says it is, and like I said, this is that part that he makes up. That's his theory. That's not the part he's demonstrating. So here he's doing a demonstration to demonstrate some properties that light has, and most of what he's saying doesn't have anything to do with what he's demonstrating. It's just saying what he says it is. And so there's a huge confusion, I guess, people have between what part you're actually proving with this experiment and what part you're just saying. All that was just made up. All that wasn't something proved by this experiment or any other experiment. The wave breaking in two and going through two slits and all that crap. There's no evidence that happened.
Where the overlap occurs, we see an interference pattern. We get a light region where a crest from one slit meets a crest from the other.
And again, very hard dark lines. No real. The pattern's supposed to be very gradual from one to the other, and it's very uneven. The lights look much thicker than the darks. They shouldn't. They should be proportional to each other, mathematically. So not even as the math would predict, the pattern doesn't reveal what the math says the pattern should look like.
In other words, where we have constructive interference, and we get a dark region where a crest from one slit meets a trough from the other, or where we have destructive interference. We can show that both slits are involved by closing one of them up and seeing what happens.
So he takes like a ruler,
The pattern of light and dark bands disappears.
and shoves it over technically one of the slits. What he just did was he took the needle, the wire, out of the experiment. It's no longer getting hit by the light, and he just turned it into a single very wide slit, which isn't going to create any kind of pattern at all. So it's the double slits were not relevant to the experiment. That's why there wasn't any envelope to the pattern, and he's misdescribing what's happening in the experiment. That's all. And they're just saying they're still misdescribing what's happening in this experiment.
With only the diffraction pattern of a single slit. So it must be that both slits are simultaneously sending out interfering waves.
It must be that both slits, so again, it wasn't anything about slits, that the two sides of the wire were interfering with the photons that passed them. That could be the rational conclusion, that yes, both sides of the wire, the photons that went close to the wire moved differently than the photons that were far from the wire. Another simple interpretation that doesn't require Copenhagen radar, doesn't require many worlds to be invented or multiverses. A simple explanation that photons behave differently when they move close to a surface than photons far away from a surface. Not a very insanely bizarre bit of speculation, but completely ignored by them. Can't possibly be the explanation. Somehow that can't be the truth.
Before I can show you that we can polarize visible light, you must first understand what this means. Let me get rid of some of this equipment.
Cool. So the only thing they've changed in doing these experiments is that they don't have that big clunky material they have to work with anymore. So that they've modernized some of the bits, but they still do it the same way in the same perversions.
Visible light. We mean that we can force the electric vibrations of all the waves to lie in any chosen plane containing their direction of motion. Now, light is transverse. That is, if the electric vibration is at right angles to the direction of motion. Then what we need to accomplish this is to have a preferred axis in a plane across the direction of the light beam, such that this preferred axis selects those waves whose electric vibrations are parallel to the axis.
So he's just giving you my analogy of the jail bars without doing it in that simple way. By just saying you create a mechanism, a filter, that will not permit certain light to get through, but has certain tolerances that will let some variations get through. He just said that, but he didn't say it like in any way that was simple.
We have such a device in this Polaroid filter. As you can see, light is getting through the filter. What has happened is that the electric vibrations that get through are lined up with the axis of the Polaroid. I have another identical Polaroid filter, which I'll put in front of this one. And I have previously arranged the two axes so that they are parallel. Light is getting through both of them. Now, if I rotate the second axis by 90 degrees.
Okay, so just understand, the jail bars are both going the same way. And now he's just going to take one set of jail bars and move it this way, so now nothing's going to be able to get through both set of jail bars.
I should expect to get much less intensity getting through to the screen. This is because the vibrations lined up with the first axis reach the second Polaroid and find there an axis at right angles to them, and therefore they should not get through. Let me rotate it and see what happens. The intensity has gone down. If I rotate it another 90 degrees,
again, you can sort of see in these experiments that when they do that, there's a part where it doesn't make any changes, no changes, no changes, and it only changes in the last 1/4 of the rotation. So you sort of get the impression that, yeah, okay, I get it. That's the tolerance, the permittable tolerance range, and all of this was meaningless. And all we're really talking about is how much a 25% that the frisbee can be off and still get through the bars.
Intensity has gone up again. And this is what we expect, because now the vibration lined up by the first Polaroid again needs a parallel axis and therefore get through. Now it certainly can't be that most of the light is a longitudinal wave. That is, that the vibration lies along the direction of motion. Because if this were so, then the axis of the Polaroid would always be at right angle to the vibration, even when I rotate it. And so no one angle could make any difference, and the intensity should not be affected. So it must be that light is mostly transverse. And if we wanted to make the experiment more elaborate, and could you...
He's just arguing that most of the photons aren't circularly polarized in the sense they'll go through any filter, because they're not spread at all. They have no difference in their positions. So therefore, so when the electron that made them, it moved this way, created created force bit 1 by moving this way. When it moved back, it created force bit number 2, and they're off by the distance of the electron, the thickness of the electron, you could argue. So that would be their polarization, would be the thickness of the electron that produced them, kind of a thing. Could be argued that that kind of mechanism is what's creating that difference, and that anything that is perfectly polarized, circularly, in the sense that it's on a perfect line, would have to be created by an electron moving a higher amount of energy and more movement, where two little elements of rays of light got loose in the period before the electron moved back to its position, that kind of thing.
A better Polaroid filter, I could show you that light is entirely transverse. I hope by this simple experiment that you now see.
Well, so now you made a statement that light is entirely transverse when he's using one source of light. Obviously different sources of light will produce different kinds of packages or rays. You'll create different kinds of rays of light using different sources of light. So even with better polarizing filters, he can't make a statement about all light because he's using one form of light, a tungsten lamp, where all the light's created by a certain chemical process of electron excitement. So lasers would be a completely different thing, and you could have a completely different expectation. So he made a declaration about all light is transversely polarized when that was probably way overstepping what he could prove with that experiment, even with perfect polarizing filters. And so he shouldn't have done that. That was stepping a little too far.
That light can be polarized, that it is transverse, and that these two properties are closely related. Let's do an interference experiment in the X-ray region now. This is a typical X-ray tube. It has a very simple structure. This is a glass envelope which is evacuated when in use. There is a cathode at one end which emits electrons when heated. And at the other end, there is a copper plate or anode. A large positive voltage is put between plate and cathode, thus accelerating the electrons to the anode. When they arrive, they have a very high...
Right, so it's just creating a huge voltage potential and making a spark, so to speak. And the spark, because you're in an evacuated tube, there's no sparking, because there's no ions to fill the void. And so you're basically sending electrons in through, across the vacuum. But there's it's not, there's no spark that you can see because there's no atoms in the way to emit the extra photons.
Energy and collide with the anode. This violent deceleration causes the emission of electromagnetic waves.
So he says it's a violent deceleration that creates the photon. So he's saying that when the electrons hit the copper plate, that the reason why they're going to release a photon is because they've decelerated. When the reason why they're going to release a photon is because they're accelerating the electrons in the copper plate. The electrons are hitting the copper and now neutralizing its charge. The charges are moving to the pole that lacks electron pressure, and the electrons are going to create more electron pressure, which is going to cause the electrons to expand. They've contracted by having the electron pressure pulled out of them by the electric charge. So the electric current is pulling the electrons. The pressure of the electrons is reducing the pressure of the electrons. So they're contracting essentially. And then when the electrons fly across the vacuum, they're going to expand the electrons, and it's the expansion of the electrons that is going to create the opportunity for photons to be released. High energy photons, because of the huge contraction created by the high voltage. So the high voltage creates a tight contraction, and now when the electrons arrive, they're going to allow the electrons to expand. That high expansion is going to release photons at high frequencies because of the compression. See, I could draw that, but I don't. Yeah, I'll draw it because it's sort of important. Alright, so I've made this argument before, but electrons are, I would argue, that this is a theoretically viable explanation of what happens, that there's force bits between the electrons. And I'm going to draw them in red, but they'd be the same color as the electron actually. And so when you're pulling voltage out, or pressure, what you're essentially doing is just moving these electrons to a tighter position. And so there's a little bit of a contraction. And that means that all the energy between them is now, if this distance contracts by a half, that'll be twice as much energy between the same number of little bits bouncing back and forth. So these are little bits going backward and forward. These are the tons. These are the force bits that make your photon. So these force bits are trapped between the electrons, and when the electrons have a wide separation, they're vibrating at a kind of high, a big frequency. And when the electrons get tight, the frequency gets tighter. So if I move these three close together, you can see now the frequency is higher, and that's exactly what happens when the electrons contract. And now if you re-expand them, and they end up releasing some of this energy through the expansion process, because it won't be even. One electron will go out before the other electrons, and that means that this energy will get released, some of this energy, as they go to their expansion points. And this is the energy that you'll see as a photon. So every chemical atom, you could sort of understand that atoms are different sizes, and you could understand that their contractions would be very different, and that would mean they would release a different color light. And X-ray essentially could be considered a color of light. We haven't given it a color, but I'm just saying it's the same idea, that you're just changing the frequency. You're changing how close the little bits are. And so an X-ray gun, like I said, is creating a high voltage. The high voltage creates high compression. And then when you release that compression, you create the opportunity for this high pressure to escape. That is the high frequency, the high vibration rate. Two tons coming out of the same place where they're bouncing back and forth at a high rate. Alright, that's probably good enough. It should be good enough for smart people.
All these waves X-rays. This is the apparatus we'll use for our X-ray interference experiment. There's an X-ray tube similar to the one you just saw in this metal can. The X-rays leave the tube here and strike a lithium fluoride crystal. The crystal looks like this and consists simply of lithium and fluorine ions in a regular cubic array. If you look at the crystal end on, it would look something like this. The important idea to get from looking at this model is that the ions can be considered as lying in planes. And in our experiment, we are going to consider the reflection of electromagnetic waves from these planes of ions. By using the ripple peg, we can show how this reflection works. Each peg represents a row of ions.
Yeah, I don't think there's much wrong with this in theory, so we'll go with this.
In the crystal. Water waves will be generated moving toward the model. The incoming wave will successively reach each of the planes. Now, the angle at which the wave enters the crystal is important. If the incoming wave makes an angle with the plane, such that the re-radiated waves add up, crest on crest, then we get a storm reflected wave, or constructive interference. And that's just what we have now. Notice that there is a distinct reflected wave leaving the model at the lower right.
So just understand, this is completely consistent with a particle model. Okay, so although he's calling these waves, these are really just reflections off atoms. So the individual atoms are creating refractions and reflections. And so there's nothing special about this. I mean, in terms of, there's no wave phenomenon here, really. This can be explained as bits of force hitting bits of atoms and reflecting in their equal and opposite angle kind of way. And there's no necessity to think of it as anything to do with a wave phenomenon or interference more than changing phases, in the sense that there's a change in the angle, and therefore that changes the phases. And at different angles, you'll have the spacing of the atoms will be exactly the phase change you need to have the consistent wave product, in the sense that it will create reflections that are exactly one wavelength off. So I could draw it, but I really don't need to, I don't think. I think you can understand. So at certain angles, the atoms will be exactly, if I take my fingers and I turn them in an angle, you can see all the black spaces disappear. A similar phenomenon, I'm changing the distance between the atoms. So as I change the distance between the atoms, I change where the reflections take place. And I'm just saying that this distance ends up being exactly the wavelength of the photon. So they're all, so when the straight waves come out of the side there, those straight waves, or those in-phase waves, converted back into being in phase, is merely because the angle you're hitting is just right, so each one is exactly one wavelength off. And that's all it is. So you're just creating refractions that are all one wavelength off. And if I tilt it differently, you can see the distance changes and the wavelength would change. So at one specific angle, it'll work. At every other angle, you'll have noise. That's all.
Right of the screen. The condition for constructive interference involves the angle between the incoming wave and the crystal planes. Only at the correct angle will we get constructive interference. We are at this angle now, so let's mark the angle as a reference.
So again, it's not about constructive interference, it's about alignment and all of them being, yes, in-phased. In-phased refractions. The refractions are all one wavelength off. The reflections off the atoms are all one wavelength off, and as if you change it, you create more noise in your in-phaseness. You lose your in-phaseness, and the noise becomes stronger. The amount out of phase becomes more than the amount in phase.
If we change the angle, like this, the individual reflections mutually cancel, and we get a very weak reflected wave.
So it has nothing to do with mutually canceling. There's no canceling. It's just that the new angle means that you're not going to create the refractions at the wavelength, and there'll be no product produced. So he changed it enough to destroy all the none of the reflections are getting out of the matrix of the atom. So this is a second argument, is we have layers of atoms on top of each other. So you could understand that when they're behind each other, because of the angle you're coming at, then you can hit the ones behind. And as you change the angle, you change your ability to hit the ones behind. So that's what we're really talking about. Is here it's all surfaces, and as I change this angle, there's no, that's so this you don't have to think of this in terms of a wave property. You think of it in terms of if you drew straight line vectors of rays of light here. If you drew rays of light instead of waves, you could duplicate the same phenomenon by just drawing those waves and doing their reflections off the atoms by specific rules.
When I again reach the correct angle, I get a constructive interference, a strong reflected wave. In our X-ray experiment, we will be able to detect constructive interference with the lithium fluoride crystal. We can see the entire experiment on this diagram. The electron beam in the X-ray tube hits the anode, and X-rays are emitted. They strike the crystal at an angle theta, leave at the same angle, and enter a Geiger counter detector. The output of the Geiger counter is put on an electronic counter. What we will do in this experiment is to vary the angle theta and look for those special angles where we get constructive interference of the reflected wave.
So merely saying that there's angles which you'll get everything will add, there'll be a harmonic, an angle where everything is exactly one wavelength changed, rather than partial wavelengths that cause internal reflections. You'll reduce the internal reflections, and everything will find a vector that allows it to leave the material. Maybe that's a better way to say it.
Now let's do the experiment. As I turn this dial, I'm varying the angle theta between the incoming waves in the crystal and between the outgoing waves and the crystal. Notice both the lights on the electronic counter and the clicks. We get a click every 64 counts. The intensity is increasing, and I'll stop at a peak. This corresponds to constructive interference between the reflected waves. As I move off the peak, the intensity drops down. And I'll continue to vary the angle. Now we're coming to a second peak, and I'll stop at its maximum. Notice that we're getting interference phenomena, which, as you know, are characteristics of the...
Right, so I'll just say it again. It's just a grid layered on top of a grid, on top of a grid. And so you're just talking about as you change the angle of the grid, you change the probability of light being able to reflect back through the grid itself without bouncing internally forever. So it's just the absence of internal reflection that is really all this Geiger counter is recognizing, that at certain angles you reduce the internal reflection.
Waveform. We're going to do a microwave experiment now, which will be directly analogous to the Young's optical interference experiment you saw just a little while ago. Only in this case...
So I would just argue that that whole experiment could have been diagrammed using ultramundane particles, using little rays of energy through a mechanical matrix, and how the little bits would shoot back out through pure reflection alone, through just a mathematical reflections. You could have diagrammed the same phenomenon in that at certain angles you get lots of stuff coming back out, certain angles you get nothing coming back out. Nothing that excludes particles as an explanation in that experiment, nothing verifying any wave interference phenomenon. It's just, again, they're tailoring an experiment to support a position, and they're just sort of ignoring the fact that there are alternative explanations, and they're just not choosing to explore them.
The wave will have a frequency of 9,000 million cycles per second, corresponding to a wavelength of about 3.3 centimeters. We'll produce the microwaves in a tool called a Crystalline. Here's one. The microwaves come out from this antenna. We pump electric charge or current up and down this antenna, and the accelerated charge sends out the waves. We've got the same Crystalline in this metal can. The accelerated charge is...
So just understand when he said we put the current, that they're putting in the frequency of the electricity. creating it. So the radar gun doesn't make the frequency is pushed into it, and it's basically just saying on off, on off, on off. It's just saying, you know, expand the electrons, contract the electrons, expand the electrons, contract the electrons. And through expanding and contracting the electrons within the atoms of the little steel bar, they're just saying, let some force loose, push some force in. Let force loose, push force in.
On the antenna, start an electromagnetic wave down this pipe. Wave reaches this point and splits, and arrives at these 2 points with identical phase. We then feed them through these 2 horns out into space. The purpose of
So now they just use 2 of those klystrons, you know, because they can make them much smaller, and 2 horns. So they just send the same signal, the same electrical signal, into 2 different horns, but they're exactly the same electrical signal, so they're producing the bits at exactly the same phase.
horns is to minimize reflection, which is caused when we make the transition between the pipe and the space. The 2 horns in this experiment will act just like double-slit did in the opposite experiment. Here,
yeah, well, that's you know, so he just kind of brushes over the little horn thing, but what it's, you know, it's basically doing is it's trying to make the light come out straight. So it's trying to focus the photons that are being produced, you know, because they are coming out in all directions. And so they can only do that with a certain amount of effectiveness.
we have a detector, which is sensitive to the resultant electric field tangent to it. We're going to move the detector back and forth through space this way, thus sampling the total electric field resulting from both these horns at each point in space.
So this is exactly like the Professor Lewin experiment. And he'll point out that again they have modulated the signal. So they're sending 2 signals. So they're not going to detect how much energy that's in any one location. That is how many actual force bits, tons, are actually getting to a location. They're completely only going to be detecting what is still on the original carrier frequency, the radar frequency, as a tone. So they have to be able to interpret the regular frequency. So any frequency that has interference in it, that is, any where 2 frequencies are overlapped on each other, they won't be detecting that because it doesn't have the carrier signal on it. It doesn't have the tone on it, so they can't see it. So this experiment is blind to anything but a clean frequency. Anything where the frequency has 2 overlapping signals, nothing. So the energy's still there. They're just not receiving it with the tone on it because they're only detecting a single frequency, not overlapping frequencies. A huge flaw in this experiment, just a catastrophically flaw, just a gigantic flaw. And they could have done the experiment just as easily by just measuring the total energy. See, there's so much energy coming out of this experiment because it's so close. So you have a ton of microwaves coming out, and you're only a foot or 2 away. So you can detect the total energy that's coming at you because of you're certainly much louder than any outside noise. And if they had just detected the amount of energy hitting that little antenna, that is just its absolute voltage, not its frequency, just the absolute voltage, there wouldn't have been a change.
The output of the detector will be fed to this meter. Now let's do the experiment. As I move the detector this way, across the incoming waves, you can see that the deflection on the meter goes through a series of maxima and minima. You can also hear it on a loudspeaker we hooked up because we're chopping the microwave 1,000 times a second.
There. He just says it like it's like a non-event. We're chopping the microwave signal 1,000 times a second. So they have a microwave voltage going in, and they're turning the on-off on and off. So they're taking a very fast on and off switch. You know, let's just make a round circle that spins and it clicks at the top. So they have a wheel going really, really fast, turning it on and off. And then they have another wheel that takes that voltage and turns it on and off 1,000 times a second. So you have something going, whatever it is, 5 million times a second, and another one going 1,000 times a second. And so the only way they can hear or detect is when they hear the signal coming from the 1,000. That's the one they're looking for, is the 1,000 click frequency. They're not even trying to detect the, well, it's not that they're not detecting it. Again, they can't know they can't they could be receiving the radar and not receiving the audio signal because the two signals are overlapped and the audio signal is destroyed.
Just as in the optics experiment, when a crest from one horn meets a crest from the other, we get a constructive interference or a maximum at the detector. And when a crest from one horn meets a trough from the other, we get destructive interference or a minimum on the meter. In order to show that this is really an interference phenomenon, we have to show that both horns are simultaneously involved in producing the resultant field at the detector. Now you'll remember we stopped at a minute.
So I think I'll draw this real quick just because it's really is important. You know, just to understand what's happening, you know, and just how wrong it is for them to use carriers, because it just complicates what should be a simple experiment. Well, I'll just get a new piece of paper, I think. Yes, I can do that. I can afford to give you a new piece of 5 million year old printer paper. I mean, you know, it's still got the little lines on it, but, you know, old dot matrix paper, surplus and such. All right, so the idea is that you have these two emitters, and they're creating an on-off signal, and the on-off signal has built into it an on-off signal. But just to understand what's happening is when the two waves, you know, are coming out, they are coming out in the sense that some go straight and some come off crooked, and these are different distances. So you can understand that they are coming off in a sense in this manner, but that's only because of the distance reality, that this distance is the same as this distance. So all the ones going sideways, so if one ray is coming from this one and one ray is coming from this one, they'll travel different distances, so their frequencies can be out of alignment because of that difference. You know, one wave is the opposite of the other wave, and you can have the opposite circumstance where it's so far off, you know, you go from here to say here, that they're both one phase out of phase, which means that they're exactly like each other. So they just create a higher amplitude of signal because the two signals aren't canceling each other. The problem is when they're out of phase and when they're 1/2 phase out of phase, because then the signal that was this becomes this. Now, if you're receiving a signal with this frequency, you can't hear this frequency. You can't detect it. So your ability to see this signal is going to be lost because this signal is a higher frequency when you're tuned to just this frequency. So their tuner is not going to receive the signal with the tone on it here because it can't decipher this as a coherent signal of this signal type, because it could pick any arbitrary places as the beginning or end of the signal, and so it won't be able to interpret the data because it's not collecting the data in the right orientation. Especially when they're out of phase, any information on the signal is also going to be out of phase. So the point is they shouldn't be using an audio signal. The point is if they just detected the voltage change in the antenna, they would realize that the voltage doesn't change. that there's the same number of photons hitting the antenna at all these positions. And it's only when you get way out here that obviously both signals would be deteriorated, and that, by the inverse square law, this signal will be weaker. But you'll have absolutely no interference displayed, in the sense that the amount of energy hitting all these locations will be exactly the same. So this can be analogized to the two-slit experiment, where they make again these assumptions about light plus light creates dark. So in the two-slit experiment, we're supposed to believe that these bars are being created, and that they don't really say this, but their argument sort of is that these are two photons that interfere with each other and turn into black, that no energy hits here. But they never really say that there's twice as much energy here. But that's what's really happening, is the photon that should have gone here goes here. They don't really argue that you only see half the light that comes out of these two slits. They don't make the argument that half the light turns into nothing. It disappears from the universe. They don't make that argument. And so clearly they understand that the energy is just being moved. So in the photon example, and again these examples these are just an on-off pattern. In the photon example, the mechanism clearly is not destruction of energy. Now in this radar example, they're almost making it seem like it's okay to destroy the energy, because we're not adding it all up, and we're certainly not going to explain how interference doesn't mean you destroy energy. It's that you move it to a different location. And so there's a difference between these two phenomena. When it happens in light, it's happening because of the surfaces. Okay, there's no surfaces in this radar experiment, understand. In light, the surfaces are bending the light, and that's why you have interference. In the radar experiment, there's no surfaces here, there's no slits, there's nothing to interfere with the light. So the only thing that's causing the effect of an on-off pattern is the fact that you have overlapping frequencies, and the overlapping frequencies make it impossible for you to decipher the signal, to collect it, because it's noise. They've essentially jammed each other, and so all you're demonstrating is you're demonstrating that you can jam a signal by creating another signal of specific off phase. So if I want to jam an FM station, I just have to send a signal that's like the signal coming from the radio station, except it's 1/4 of a wavelength out of phase, and it'll just jam the FM station. Your radio won't be able to detect the signal anymore. It won't be able to pull it out of the noise. But I haven't changed the amount of energy. I've added more energy, actually. So there's more energy, from the signals. They didn't destroy each other in any way. They've just made it impossible to tune to the energy. The energy has lost our capacity to tune it has changed. And again, if I put just a plain antenna up and collected just all the signals from the universe and measured it as a voltage, I would notice no change in the voltage. So this is an experiment I think I can do. I just have to get the right hardware to demonstrate it. But I really should be able to do this with two good sources and just point out how the energy didn't disappear. It's still there. You've just created an experiment where you don't receive the energy when it's noisy. And that's all. You've just shown that there's noise in certain locations and no noise in other locations. You haven't shown that anything has interfered, quote unquote. Resuming.
Let's close one of the horns and see what happens. The intensity on the meter went up. This means that the field from this horn can no longer cancel the field from the other. Let's go back to a map.
So it just means that the one horn is no longer jamming the other signal. Therefore, that signal can now be interpreted by the receiver. It can see it, and that's all that happened. And again, if they were just measuring what the antenna received in terms of actual force bits hitting it, if that's what they were measuring, that the needle would have actually gone down, because now you've reduced the amount of energy hitting the antenna. The only thing that he changed there was he's changing how much noise the antenna is receiving versus signal. So he changed the signal to noise ratio. He didn't change the amount of energy.
Now again, close one of the horns. In this case, the intensity on the meter went down.
Yes, and it went down kind of a lot. But anyway, so that's completely obvious. So yes, now it's less energy. It was already in a non-noise position. He closes one of the sources. There's no noise that was being created, so therefore he just cut the signal in half. In my version of the experiment, that would have just meant the needle went down because there's less photons, there's less tons hitting the antenna. Obviously.
Because we closed one of the horns, thus leaving only the intensity due to the other one. It's easy to show that microwaves can be polarized. If we place a screen like this between the horn and the detector, you can see that in this position the intensity on the meter is relatively unaffected. But if I rotate the screen by 90 degrees, the intensity on the meter drops almost to zero. The reason for this is it depends on which way you think they're actually being polarized. So again, this has the very look of the jail bar example. Clearly, the polarization, the difference in the range of where the tons are coming from is significant. But another factor you have to take into consideration. I'm making a video. You're just going to have to wait. So the only thing that changes is where was I? When you're doing this radar experiment, the difference is that in radio that they're not rays. They don't have to be lined up. It's just about an amount of energy, a total amount of energy that hits the surface. So it's not like the photons have to actually be at frequency because they're all in phase. So an electron can receive a photon from two different locations, very different locations, even at different angles, and consider it a signal. So you have to think in terms of the filter isn't disrupting the same. So again, light is different than radio waves, in the sense that at high frequencies it's very different than at low frequencies, because there's different things that are going to interfere. Electrons interfere with photons in a dramatic way, where at lower frequencies they're not going to, the electrons are going to have a completely different behavior in terms of they're not going to recreate a radio wave. They're more likely to block it and absorb the energy. So there's a real, in the two-slit experiment, very little of the light's getting absorbed by the electrons near the surface. But you could argue that in radio waves, a lot of the radio waves could actually be being absorbed by the material substance. And that is intuitive to what we understand, that everything absorbs radio waves, where a lot of things reflect light. I guess that's one way to say it. You're changing what's causing the effect. Reflections versus absorptions. I guess I can put it that simply. So yes, it's the same phenomenon you're detecting, but you're detecting it for a different reason, because there is a thing called absorption that's more significant with radio waves, where reflections are more significant with photons. Reflections, quote unquote. This is that in the second position, the electric field was parallel to the wires. This set up strong currents in the wires, which converted much of the microwaves to heat. In the first case, the electric field was perpendicular to the wires, not much current flowed.
Yes, so it's just about that absorption thing, that the electrons are more likely to be moved in one position than in the other position. So in being off phase, that is, the antenna is shaped this way. It emits the stuff more densely in this plane than in this plane. So there's more radiation coming in this plane than in this plane. And all you're doing is changing a filter, which basically is going to make the light from one plane more difficult to get through and the light from the other plane easier to get through. But you have to understand that the polarization of the radar is likely in these in a longitudinal. It just has to do with its intensity. It isn't the actual polarization of the photons themselves in the sense of the rays. It's the polarization of the emitter in terms of its position. So let's say if the emitter was a bar and it's shooting the stuff out and it's getting reflected by that horn, you're going to understand that there's still going to be this bar part. So there's going to be a strong signal, a denser signal this way than this way. That's all I can say, I think.
And most of the microwaves got through. You have noticed that in this experiment, the microwaves were already polarized as they left the horns. The important thing is that we could polarize them, just as we were able to do with light in the optics experiment. And once they were polarized, they retained this property as they traveled through space. We showed you this when we placed the screen at some distance in front of the horn. This meant that...
Right, yes, but that's again just saying the same thing over again, or saying the same thing twice. Clearly you could change the horns and change the polarization of the antenna essentially. So I can move an antenna different angles, and I'll change where you have to hold your receiving antenna, because again there'll be a denser signal in certain planes.
The microwaves had to carry their polarization property with them as they traveled to the screen. Incidentally, it's easy to measure the wavelength of microwaves. If we place a reflecting screen behind the detector, we can pick up a standing wave pattern. And by measuring the distance between minima, we can get the wavelength of microwaves. Let's go do it. I'll put up a reflecting plate in back of the antenna. The wave coming out of the horn comes down this way and bounces off this plate. At the position of the antenna, we have both an incoming wave and a reflected wave.
Right. So he's just basically creating another out-of-phase wave. So, the stuff that doesn't hit the antenna the first time bounces off the reflector and comes back, and you can make it to be exactly one wavelength, or you can make it, again, a half wavelength or some other wavelength. So he'll probably come up with this idea of every 3 centimeters it'll be on phase.
As you know, the sum of two such waves gives a standing wave. I'm going to move the antenna in this direction and follow its position.
There's not really a standing wave. There's a perpetual source. The source you can hear in the background is perpetually shooting pressure, and there's no such thing as a standing wave out of nothing. It's made out of something. The standing wave is a byproduct of just having waves in phase.
With this pointer. In order to allow me to measure
harmonics,
the standing waves, I'll put this centimeter stick behind it as a scale. As I move the antenna, we go through a minimum, maximum, and let me stop at a minimum and mark the scale.
So again, this proves my point that this doesn't need to be interference. He's just basically jamming the signal, not jamming the signal, jamming the signal, not jamming the signal. That's all.
Now I'll move the antenna to the next minimum. And mark the scale again. The difference between these two marks is just 1.65 centimeters. As you know, standing wave minima occur every half wavelength. This means that the wavelength of these marks...
Okay, so he's doing the half wavelength thing, so if that's a half wavelength, then right, so he's doing the interference thing, so it would be twice where he put these marks. Because he just marked a half from interference to from signal to no signal. You have to measure from signal to get the full length.
Microwave is like 1.65 or 3.3 centimeters.
Yeah.
The most common use of microwave, radar, is probably familiar to most of you. In radar, we shine microwaves onto an object and measure the time it takes for the microwave to go to it and come back. If we take half this time interval and multiply it by the speed with which microwaves travel, we can calculate the distance of the object. This speed turns out to be exactly equal to the speed of light.
So I would argue again that it would have been nice if back in 1950 whatever, that the 61, that they sort of figured out that maybe we shouldn't call it the speed of light anymore because it's the speed of force, and they should have called it the speed of force because all the forces move at this speed and light's a force. I think that would have helped, was to call light what it is, a force, like magnetism, like gravity. It's a force. But again, that's too particle. That's too unifying, and they really, you can't make bent space into one of these kind of forces. It doesn't work because this has particle duality. They don't even accept any notion of a particle duality when it comes to gravity. But the truth is, it's particles in gravity, it's particles in magnetism, and it's particles in the electromagnetic spectrum.
Our last experiment is in the radio wave part of the spectrum. Here we will work at a frequency of 140 million cycles per second, corresponding to a wavelength of about 2.1 meters. Because of this large wavelength, we obviously have to work with much larger physical apparatus and in a larger area.
So now the little bits are going from being 3 centimeters apart to being 2 meters apart. So huge difference. And again, something to understand that every time you make those differences, you're changing what's going to affect the little bits, because they're not coming at a high frequency. They're not coming as in alignment. Their polarization is getting even more dramatic. As you increase the wavelength, you also increase the dimensions of the polarization.
This large field will be perfect for our experiment. Aside from the larger equipment which we'll use and the lower frequency, this experiment will be identical to the one you saw with microwaves. There are 2 antennas set up about 20 feet apart, which in this experiment will take the place of the 2 horns in the microwave experiment. The antennas are fed from the same transmitter, thus making them coherent sources of electromagnetic waves. We're going to pick up the resultant electric field from the 2 antennas with a similar one here.
Right, and it's exactly the same setup. So again, the little speaker, they're only going to measure what signal they can first receive, in the sense that it's not jammed, and that's the one you could possibly hear. And even if they could receive a dual signal, one superimposed on the other, the information, the tone signal, may be disrupted by just a tiny change in that receiving, and therefore there's no tone anymore. The tone could also be at a higher frequency. Well, I don't think that's an issue, frankly. It's just that they're still receiving only a signal from which they can actually pull signal out of noise, and they're not doing that. They don't have any capacity to receive 2 incoming signals that are out of phase, and therefore the audio signal is out of phase. They have no capacity to receive those 2 out of phase signals, one or the other. The 2 of them combine and cause noise, and there's no signal received.
The way the waves come out from these 2 sources is just the way the Crystalline antenna sent out microwaves. What we're doing is to pump electric charge from the transmitter into and out of the antennas and back and forth at the rate of 140 million times per second. It is this accelerated charge which sends our electromagnetic waves off. Now, if our ideas of the interference of electromagnetic waves are correct, we'd expect to find reasons.
So, just for illustration, again, he says 100 million times a second. Well, he was doing it with the radar a billion times a second. So, I'm just saying the radar experiment was a much smaller wave. So, this wave is a much more relaxed wave.
Of constructive and destructive interference in the space here in front of the 2 sources. So what we're going to do is to move our pickup antenna back and forth in space, thus sampling the resultant electric field from the 2 sources. We'll convert the received signal into sound on this loudspeaker and also into a deflection on the meter. The reason you can hear the sound is because we're chopping the transmitter signal 1,000 times per second.
There. We're chopping the transmitter signal 1,000 times a second. He just kind of throws it out there, but doesn't go into an explanation that essentially guaranteeing that, the audio signal will only be heard when we can actually detect the carrier signal. And the carrier signal can still exist, but it can be jammed.
Now let's try the experiment. As we roll along, moving the detector, once again, we go through a series of minima, maxima, and minima. Now let's try it again. And I'll stop at a minimum.
Right, so, I mean, this is so redundant, and sorry to also include it, but it's on the tape, so I just figure we'll play it, just so no one says I deceived anything. But this is exactly the same experiment with exactly the same flawed understanding of what's happening.
To see that this is really an interference effect, let's disconnect one of the antennas. John? You see the intensity has gone up, both on the meter and in the sound level. This is because we disconnected one antenna, and so we...
Yes, and now disconnected the interference. This disconnected the jamming. The one antenna was jamming the other signal because in most locations, and it was over... That's why it got so much louder also, that in most locations there was a combination of two signals and they couldn't be deciphered by the receiver. The receiver can't figure out these two... There's two signals in there. It's saying that's a megahertz signal. And it's like, no, it's not a megahertz signal. It's two of these signals. These two signals. It can't see that. The receiver is saying, no, that's high megahertz. Ignore it. The band filter gets rid of it. The high band filter. Saying, get rid of that. That's noise. But that was actually the signal. And once you get rid of that noise, then it's picking up even more signal because it doesn't have this noisy crap fucking with it. It doesn't have anything messing with the other signal. That's why it got louder. Is because you got rid of the noise. You got rid of the thing that was causing the band filter to kill most of the energy. To say, no, that's the wrong frequency.
Can no longer cancel the field due to the other. Let's reconnect it. Our intensity is down again. We're at a minimum or a point of destructive interference. Let's try the same thing at a maximum.
It's just jamming. We've now introduced the noise signal again because the two antennas are out of position, different positions. That is, they're on different phases now because they're sending a signal from a different position. Just as I pointed out inside the atom, that the light being created is being created from different positions, and those different positions will automatically have a different phase, and so it's very hard to create a perfect phased light because you have to just create on the very surface of a material.
And let's disconnect one of the antennas. Now you see the signal has dropped. This is because we removed an antenna, so we're receiving the field due to only one, and so we get a smaller signal. Do you see?
Yeah. Again, they just disconnected the element that was causing noise. And obviously when you disconnect one of the antennas, you reduce the total intensity of energy, so obviously the signal went down because there wasn't two signals anymore.
Once again we have wave interference, this time the radio wave region of the electromagnetic spectrum.
So again, every time there's an on-off, every single time there's an on-off, they think it's interference. It's just the way they think. They can't, no imagination in terms of figuring out that it could be some other mechanism. There's not even a bit of speculation about a possible alternative explanation.
I want to show you, and that is that radio waves are polarized. The waves being transmitted by our antennas are polarized such that the electric disturbance is parallel to the metal rod or antenna. This is because we're pumping charge or accelerating it back and forth along the rod, and it is this accelerated charge which starts the wave going parallel to the rod. We can show the polarization of these waves and actually receive by rotating the antenna. John?
So he would argue that the charge is going this way. I would just argue that the antenna creates a density in that plane. So there's more signal coming out in that direction, and clearly any polarizing effect would be lengthwise, not widthwise. Very small width, very long length.
To rotate it by 90 degrees. You see, as you rotate it, the intensity drops, and at 90 degrees, it is gone down to 0.
That's because your receiving antenna is very thin in the direction of where most of the signal is. So most of the signal is going this way, the density, and your receiving, your antenna is very thin in the dimension of the thickness.
This is because the antenna is now sending a radio wave polarized, such that the electric field is perpendicular to the antenna that is receiving. Because they are perpendicular, you get a minimum received signal. Let's rotate it by another 90 degrees and see what happens. You see, the intensity has gone up again. This is because the two antennas are again parallel. The wave being transmitted is polarized, such that it arrives at the receiving antenna with its electric surge parallel.
Again, it's just this obvious thing. It's very thin this way, so it can't be making much going this way. It's very long this way, so it's making lots going this way. I mean, yeah. You have to be in line with the strength of the signal.
Of the antenna, and is now fully received. Let's see what we have accomplished. By doing a simple interference experiment in 4 widely separated regions of the electromagnetic spectrum, I've been able to show you that the interference effects arise from waves, that the waves are transverse and can be polarized.
I don't see, as I pointed out, these are the semantics problem, but no, they're not waves. They're groups of stuff, maybe you could call it. They're aligned bits, but it's not a wave.
They arise from accelerated charges and travel with the speed of light. It is due to these time properties that we believe in the unity of the electromagnetic spectrum.
Whatever the unity means, but obviously the spectrum could include gravity and magnetism if you understood the difference between when you polarize this very force, I mean when you segregate. But you'd have to understand that this force has a complementary force that affects protons. And you're not paying any attention to the proton force because the protons don't get to move a lot. The electrons move a lot. Protons don't get to move a lot. Alright, so we've completed the task, I believe, and made our points, I think. So again, any reasonable counter-arguments? I would love to have some sort of conversation with somebody who wants to defend the interpretations that have been, as again, 60-year-old interpretations, defend the way the experiments are conducted, defend in some way that somehow the interpretations I've given you, explaining that the double slit he did wasn't a real double slit experiment, it was just the single wire experiment. You know, if somebody wishes to defend their interpretation and that they have it right, yeah, I'd like to have the conversation. So comment below or something that you're willing. Make an argument. But I think this is why the fundamental axioms of physics are wrong. They're just wrong. And they're wrong in an insignificantly significant way. I mean, clearly causes, you know, saying that somebody's dead and figuring out that it was a butter knife versus a steak knife, maybe that's not important. But I would argue in physics it probably is. It probably isn't. There's probably lots of stuff science is missing by having these wrong assumptions about fundamental causes.